Hi everybody, we're going to look at our lesson for the weekend. First period you will want to watch from this point on, and fourth period you want to fast forward until we get to the part where it picks up where we left off, because I did not get this far with first period, so they need to see this. So alrighty, in this situation they want us to find the equilibrium concentrations of all the species and the value of K. We have this chemical reaction here where we have PCl3 being made and Cl2. I do think we got a little bit into this in first period, but what I'm going to teach you how to do is use an ice table or an ice box to work this problem. And how that works is it basically lays out all the information that you have, and it helps you see where you need to go and how to find these numbers. Now, ICE is just a acronym for I stands for initial, C stands for change, and E stands for equilibrium, and I'll show you how that comes to play in this box in just a little bit here. But if we look at the problem, it says initially, or it says we have a 1 liter flask. It has this many moles of PCl3 and this many moles of PCl5. So we have some of this species and this species, but we have no Cl2 present. Then it says after equilibrium is reached, so some time has passed, the concentrations are measured, and they measure that they have this many moles of Cl2 in the flask. So if we think about that, we're starting with some of both of these, but we have no chlorine. That means the reaction is going to be proceeding in the direction of going to the right, because we're going to be making Cl2. So that kind of gives us an idea of what's being formed and what's being consumed, which will come out in our ICE table. Our goal, we need to find the equilibrium concentrations. We will find that using the ICE box. We'll look for the values that will go in what I call the E row. We'll see that in a minute. And then once we have those equilibrium concentrations, then we can plug that into an equilibrium expression, which we would write from this equation here, and we can solve for K. The key factor here is this 2 times 10 to the negative third moles of chlorine. That's going to really help us fill out this table. So the next slide is going to talk to us about what we would need to do. So the first thing you need to do is find the concentrations, because right now we just have the moles and the volume. Then we are going to, I don't know what is going on here. Why this isn't coming up. Sorry, I'm probably going to have all kinds of technical glitches today. I apologize for that. So then the next thing we're going to do is define what we are starting with, look at the change that takes place, and then we can determine the equilibrium concentrations. And that's where our ICE box comes in, or our ICE table comes in. I'll teach you all about that. Once we find those equilibrium concentrations, then we can plug those values into our equilibrium expression and find K. So this is the first thing we're going to do, is find the concentrations of each substance. So the moles were given, our volume was a liter, so there's our concentration of PCl5, here's our concentration of PCl3, and then we have no Cl2. I'm going to take this and enter this information into an ICE table. Now, what I usually do when I write an ICE box or an ICE table is I write the balanced equation at the top, and I don't have the arrow here and the plus sign here. I usually would do that. If I did it on the board, you would see an arrow here and the plus sign there. Then down the side here, I'm going to write the letters I, C, E. Gosh, I hope you're going to be able to see those as they appear. So the I here stands for the initial conditions. So this is my concentration of PCl5 originally and PCl3, and we had no chlorine at all. The next row is the C row, which indicates the change that took place. Now all of this information is coming up and it probably isn't going to make any sense, but let's walk through it. It said at equilibrium that we had 2 times 10 to the negative third moles per every liter of chlorine. So that means at equilibrium, we end up with that amount, but we started with none. So that means chlorine was actually formed as the reaction took place. So I put a plus 2 times 10 to the negative third molar, indicating that's how much it changed by. It went up by that amount. Now, keeping in mind, if we're moving in the direction of the products, not only was chlorine made, so was PCl3. Now, how much PCl3 was made is dependent upon the mole ratio here between the chlorine. I know I made 2 times 10 to the negative third moles per liter of chlorine, and this is a 1-to-1 ratio here, so I know that I also made 2 times 10 to the negative third molar of PCl3. Now what formed those was the PCl5, so this had to be consumed in order for these to be made. So therefore these are all in a 1-to-1 ratio. For every one of these that's consumed, one of these is made and one of these is made. So that means the PCl5 went down by that same amount that the other two went up because of that 1-to-1-to-1 ratio there. So the change that occurs, which is my C row, is the PCl5 went down by that amount, and the PCl3 and the Cl2 both went up by that amount. The E row comes from adding the initial and the change together to find out what is actually present at equilibrium. So if we take a look here, this is actually the amount that was reported at equilibrium, and that comes from knowing that we had none of it to start with. It ended up with that amount in equilibrium, so this is the change. If you add this together here, you're going to get that value. The PCl3 went up by that same amount, so you take this value and the change value, and you get our equilibrium value of 0.3 molar. And then the PCl3 went down, hence the negative sign, by that amount, and so its ending molarity is 0.0067. So as you see here, when we fill out our ice table, it is really important for you to have your plus and minus signs indicating what's being consumed and what's actually being formed, so that when we do our addition from the C row to get the E row, we get the correct value. And that should make sense. This went down by 2 times 10 to the third molar, so this value should decrease, and these values should increase if they were made. Now, they asked for the equilibrium concentrations. That was one of the parts of the problem, and guess what? This E row right here is telling us the concentrations we now have at equilibrium. So these are our answers for each of those species. We can report those separately, and you'll probably see that in the slide in a minute. The other thing is they asked for the K. Well, to find K, we need to write our equilibrium expression from our balanced equation. So we should see that right here, so equilibrium expression. Taking the values from the E row, that last row of our ice box or our ice table, we plug those values in the respective positions, and we can calculate the K. Now, this is looking at another scenario here. It says if no concentrations at equilibrium are given, they don't tell you what you have at equilibrium, we're going to use the mole ratios, the stoichiometry of the reaction, and the initial concentrations to help us determine what's happening at equilibrium. And there's a variety of different problems that you'll run into. So we're going to include Q here in a minute. And let me go back and look at this problem and tell you why we didn't have to worry about Q. Now, remember what Q is. It's the reaction quotient, which tells us either whether we are not at equilibrium, or whether we are at equilibrium or not. And then if we aren't at equilibrium, which direction are we going to shift? Are we going to start making more reactants? Are we going to make more products? We don't need Q for this particular problem here based on our initial conditions. Whenever you have what I call a hole in one of our species in the reaction, here's our hole. We don't have any chlorine at the onset of the reaction. Well, that's really going to tell you what direction the reaction is going to be driven, because when you reach equilibrium, the point of being at equilibrium is you have some of each species present. Well, if you start with none of this present initially, then you know as it goes to equilibrium, it's going to start making this. So basically that tells us that the reaction is driving towards the product side, and that hole will get filled. And that's exactly what happens here is the PCl5 starts turning into these things, and we start creating the Cl2, and then at equilibrium we have some of each. So there was no need to use Q. What Q does is tells us if we don't know which direction the reaction is going to shift to reach equilibrium, we use Q to determine that. Well, we didn't need it in this case because looking at our initial values, it's going to shift in the direction of where that hole is, where we have none of one of those species. And yes, you can have a reaction actually shift to the reactant side in these problems. That means that if we would have maybe no reactant here, none of the PCl5, but we would have both PCl3 and Cl2, so the reaction actually could shift to the reactant side, and that means our PCl3 and Cl2 would go down and our PCl5 would be increasing, but we can see an example of that later. So another type of problem here we have. It says carbon monoxide reacts with steam to form CO2 and H2. They give you a K value, so we actually are not going to be solving for K. They give it to you. They say calculate the equilibrium concentrations of all species if 1 mole of each component is mixed in a 1 liter flask. Again, we do need our molarities when we do our ice boxes. We are going to use molarities, so that's why we're going to use our moles per liter. We also need a reaction. So here's our reaction. Oftentimes it's provided for you. So what we're doing in this scenario is we have 1 molar of each one of these things present at the onset. Our goal is to find how much we have at equilibrium once the reaction runs until those concentrations are no longer changing. To do that, we have to figure out, well, are we going to be shifting to the right, to the product side, or are we going to shift to the left, the reactant side? Now, where that comes in is using our Q value. Remember, we looked at how we could compare K and Q, and that would give us our indication of which direction the reaction was going to shift. So that's what we're going to need to do. First thing is we find our concentrations. That's pretty easy to calculate here for each of these species. Then we're going to use our Q. We have to calculate Q and compare to K. So that's what we're going to see here in a minute. After we figure out Q and figure out if the reaction shifts to the left or to the right, then we can use an ice box and proceed from there. So let's see how this all plays out. Determining the concentrations, find Q. The reason we need Q is because we have some of each of these present at the onset. So you can't just look at the numbers you've got to determine whether we're going to shift to the right or left, because there's no holes basically as in one of the species. We'll use our ice box. Then once we get our concentrations that fall in our equilibrium row, then we can solve for those concentrations. We are going to use an X here. I'll show you what that means in a second as we go through our ice box. Now our K was 5.10, so that we've got to keep that in mind because I don't think it shows up in the slideshow. All right, so the initial concentrations, very easy to find out by, it's 1 for each one. Now what we're going to do is fill in our ice box. This is what we're starting with, 1 molar of each of these. We'll put those in our ice box. And then we also need to figure out, well, is the carbon monoxide in the water increasing or decreasing? Is the carbon dioxide and hydrogen increasing or decreasing? That's where Q comes in. So initial amounts, remember those sub-naught, these zeros are meaning at initial conditions. Plug those values in. That's a really hard math problem. Might need to get your calculator out for that one. And we end up with a Q of 1. Now, if you remember, I mentioned K was 5.1. So if we wrote 5.1 here, where this K value is, and had 1 here, you can see that 5.1 is bigger than 1. And remember, when we compare K and Q, I suggested putting your K value first and then Q, because your sign here then tells you the direction of the shift. So that means we need to create more products and consume reactants to reach equilibrium. Okay, so, but we don't know anything about how much is being used and how much is being made. So that's where the X variable comes in, the X vector comes in. So here is our ice box. Now you're going to go, what the heck is all this? Let's talk about it, okay? Usually, if we were doing this in class, I'd write this out step by step for you, but we don't have that advantage today. Here's our reaction. Okay, these are our initial amounts, hence the I row. Okay, now where the heck did all of this stuff come from? What are you doing with those X's and the pluses and minuses? Well, I mentioned before, we don't know how much the carbon monoxide is going down, how much the water is going down, and how much the carbon dioxide is going up and the hydrogen is going up. But I do know what ratio they are going down and going up based on our mole ratios. It's a 1 to 1 to 1 to 1 ratio. We also did decide, based on the comparison of K and Q, that the reaction is going to shift to the right, and we're going to create products, which is why we have a plus sign here and a plus sign here, and that our reactants are going to be consumed, hence the negative sign and the negative sign. The X's are our unknown amounts. We don't know how much it's going to drop by or how much it's going to go up by, so we put an X in there. The problem did not give us any indication as to how much of these things we had at equilibrium. It didn't say one of these changed by a certain amount, so we have to put in an unknown variable there. And the reason they are all 1 x's is because they're all 1 to 1 to 1. So if we went to pretend land here, and let's say there was a 2 here in front of this carbon monoxide, we would still declare these, all of these that have a 1 coefficient, we would assign those an x of 1. But this would go down by twice as much as the water goes down. So this right here would have a 2x present. Okay, so we do look at those mole ratios to figure out how these changes are affected. Now, it isn't really a 2, so let's erase the ink on the slide so we don't get confused by that. So what I've done is I've used my Q, to determine direction of shift. I'm going to make products. I've assigned an unknown because I don't know how much the change is, and I carry those values down by adding my I and my C row to get my E row. Now, the question was, how much do we have at equilibrium? Well, right now I've got a bunch of x's in there. So how in the world am I going to find what that x value is? Well, I do know the ratio of the products to reactants because they gave the K value. The K is 5.1, so I do know the ratio. So if I plug my 5.1 and these into my equilibrium expression, I should be able to solve for those x's. So here's our equilibrium expression. Our value for K was given, 5.1. We have each of these equilibrium values here with their unknowns are going to be placed into the respective positions in the equilibrium constant or equilibrium expression. And that's what we're doing right here. So this is my carbon dioxide value, this is my hydrogen value, this is my carbon monoxide, and my water value. Okay. Now we're going to look at the algebra here. So if this is just one big algebra problem right here, and you think, oh boy, what do I do with that? I know I've done it before, but I've forgotten. If you notice, by these two terms multiplying by each other, both terms are exactly the same. So that's where the square comes from. This times that squares. So we really have what we call a perfect square, if you remember that. The numerator, you could take the square root of that. And this, you can take the square root of that, and you get 1 plus x and 1 minus x. That's what we call a perfect square. I know I didn't do the mathematically terms correct. But all of this right here equals 5.1. So if I take the square root of both sides of this equation here, which is basically what I'm doing here. Now this step here, they've already taken the square root of these squared terms, which gave us the 1 plus x and the 1 minus x. They have yet to calculate what the square root of 5.0 is. You can do that in your calculator. Once you get the square root of 5.0, you can plug that in here. And then it's a matter of cross multiplying and solving for x, making your like terms come together, getting x on one side. Once you do all the mathy stuff here, all the algebra stuff, you find out that x equals 0.387 molar. So a couple things you just have to refresh when you're doing these types of problems are these perfect squares. That's one thing to go back and look at. And just the algebra part. I know it's been a little while. You guys are in more advanced math than that, but need to recall those skills that you have that you don't remember you have. Anyway, so after doing the math, we get x equals 0.387 molar. Now this right here is not the final answer. This is simply the value for x. So to get the actual equilibrium concentrations, this needs to be substituted into each of these terms in the E row. So the 1 molar for the carbon monoxide is actually going down by 0.387. So is the water going down by 0.387. The carbon dioxide is going up by 3.87, as is the hydrogen going up by 3.87. And then we'll see that on the next slide, I'm pretty sure. Yeah, so, and what they did on this slide is they just simplified things. The carbon monoxide and hydrogen, or the water concentrations were equal to each other. So they just set that in saying those are equal, and so they didn't have to write it multiple times. So here's the concentration at equilibrium of the carbon monoxide and the water. And then the carbon dioxide and the hydrogen as well also are the same. So they just simplified by They consolidated is what they've done. And they add that value of 0.387 to the initial concentration, and that's our concentration at equilibrium. So it's another version of equilibrium problems using an ice box. So the first one that we did had initial amounts of everything except for one species. So the direction of shift was determined by filling up that hole. Which side of the arrow is the hole on? That's the direction it's going to shift. This problem here, we had starting amounts of everything, so we had no hole initially, so we had to find Q, and Q helped us determine the direction of shift. The other issue we ran into is we did not know how much the change was. They didn't give us any indication of that, so then we had to put in this variable of the unknown here. And then from that, we used our K, which they provided for us, plugged it into our equilibrium expression, did that big mathy problem there. A lot of your problems are going to look like that, very, very much the same. And oftentimes you will have this situation where it is a perfect square. Those are pretty easy to handle. There are times occasionally when there isn't a perfect square and we end up having to use your quadratic equation. I know that's like, oh, the quadratic equation. I don't know if I'll get to that today or not, but that is another way to solve these problems if you get done with this and you have a squared term, but it's not a perfect square. And then on Monday, what I'd like to do is cover with you something called a simplification. And it's a little more complicated than what I want to talk about right here. Let's look at another problem here and see if we can work it together. So this is problem 1311. It's nice if you have your book with you because I don't have the entire problem written up here, I don't think. Maybe I do. So let's see, we have a reaction, equilibrium constant is given, so here's our K. Be careful, they give you words, they didn't give you the letter K, so don't like breeze over that. Realize, what is that number? Okay, that's your K, equilibrium constant. We have 3 moles of each component added to a 1.5 liter container. Oh good, it's not just a 1 liter container this time. It says calculate all the concentrations at equilibrium for each species. Here's our reaction. So we're going to use an icebox again. They have provided our K, and what they're saying is initially we have, what is 3 divided by 1.5? So we have a 2 molar concentration of each of these species initially. They give no indication as to any kind of change or an equilibrium amount of any of the species. So this is one where we're going to have to plug in an unknown. We don't know that change, so we're going to have to base it off of our mole ratio here. So we get to see that too in play here for this problem. All right, initial concentrations, find Q, so we can figure out what direction are we making reactants or are we making products. We'll use our icebox to do that. And then we can plug our equilibrium values into the K, with the K into your equilibrium expression, and then solve for X. We already kind of did this before. We started with 2 molar of all of your species. Let's figure out direction of shift. So we don't have the equilibrium expression written out for us, but I think you have done that enough. You could figure out what that equilibrium expression is. It's in your book on page 627 if you want to look at it. Then we take these values, this value here, which is our initial amount, plug it into each of those spaces into the equilibrium expression. We find out that Q is 1. Well, K was basically 115. So we have 115 for K, and Q is 1. So in this case, K is quite a bit bigger than Q, so we would be having a greater than sign, which means we're pointing to the right, we're going to make products, and we're going to consume reactants. All right, now this is what we're doing here, is we're figuring out, well, what kind of change is taking place? And I think it'll be more evident when we look at the icebox. But H2 and F2 are both a 1-to-1 ratio. When you do these types of problems, I always assign the species in the reaction that has a 1 coefficient as our X. And then everything else that has a 2 or more coefficient will simply be that multiple of the X. So here we go. We look at our icebox here. There's our equation. These are our starting amounts that we calculated from the 3.5, was a 3 moles in 1.5 liter, I think. So that's where our 2 molar comes from. We decided we were shifting to the right. Now, how do we assign those unknowns? Notice these two have a coefficient of 1 and this has a coefficient of 2. So I put 1x here, 1x here, and a 2x here. Then our sign here should be positive because we're making products. These should be negative because we're consuming reactants, so these are going to go down. And then you simply add top to bottom on each of these. And so here are equilibrium values here. I know they're not an actual quantity, but they are what we will plug into our equilibrium expression. I don't know if I've got the oh yeah, here we go. So here we have our equilibrium expression written out. Our K value, we're using the K value because we're talking about equilibrium. So these values here came from our E row, all right? Remember, when you write your equilibrium expression, this coefficient becomes an exponent, so that's why this term here is squared. Please don't forget that. A lot of students forget that. And then these values here came also from the icebox. Now, if you look at this, the top term squared, these two multiplied by each other also is squared, so we have another perfect square taking place here. So again, to solve this, I'm going to take the square root of this side and the square root of my K. And this is the result from taking the square root of this side. They did not solve for the actual value of the square root of that. Then once you figure that out, then you can move everything around, combine like terms, solve for x. There's your mathy part that isn't shown here. And they find x to be 1.528. Again, that is not the final answer. They want us to find the actual quantity that goes in here. So the 2 molar went down by 1.528. So did the fluorine. And the HF went up 2 times that amount. So we've got to remember, okay, the mole ratios here. These are the only two that are 1:1. This one is 2:1. So we incorporate that in our unknown term here, which then gets incorporated here. So if we see how the math plays out here, there's our H2 and F2. Remember, they're just consolidating here because they were identical starting amounts and they changed by the same amount. So both of them will end up being the same, 0.472 molar. And then our HF went up by 2x. So we take this value, multiply it by 2, and then add it to our 2 molar. Hence, we have a 5.056 molar result here. So right here, our green numbers here are our final answers. So tricky thing is make sure once you've solved for x, what did you really solve for? Is that my final answer, or do I then have to go back to my E row here and plug that in to find my concentrations when we're done? Nice way to check this out if you want to double check that you did your math right. So these are the equilibrium concentrations. Well, here's our equilibrium expression and our K. If we take these values and plug them into our equilibrium expression here, do we get 115? That's one way you can double check your work, say, did I make a big mistake or not? These are pretty hefty problems, you guys. It's going to take a little bit of work, especially if you've got to refresh on the algebra there. And especially when we look at those that have quadratics in them, I'm only going to give you maybe 1 or 2 of those that you have to work with. They're a little bulkier, etc. And then I will show you the simplification for the 5% rule on Monday, which will actually keep you from having to do the quadratic. It's just a really helpful thing, and you'll use that. That gets used a lot in equilibrium problems. So what this is, section 6, is really just going through what are the main steps that you use for solving equilibrium problems. There's a text box on page 628 that lays it all out for you. You want to make sure you have a balanced equation. Always write your equilibrium expression, and I just think that's a great way to kind of pull things together for you. Know what you're actually using to solve your problems. Figure out what you've been given. Okay, do you have initial concentrations? If you do, list them in your icebox. If you don't have a hole in one of those species, calculate your Q so you can determine your shift. Are you moving left or right? Then if you don't know the amount of change, they haven't either given you an equilibrium amount or they haven't told you how much something changed by, then that's when you use the x variable in your change row, using your Q as to which side is going down, which side is going up, which is positive x, which is negative x, etc. And then plugging as you need to with your E row. So they all pretty much have the same general setup for these. It's just a matter of the reactions are a little bit different. Maybe you're shifting to the left. Maybe they're not all 1-to-1 mole ratios, etc. So they do give you a few different varieties there. I think this problem is using pressures, and I think this actually does use the quadratic. I think maybe I will press on and do this. That way on Monday we can jump right into our 5% rule, which will make our math so much easier. But in this problem, this is on page 630 in your textbook. It says this one we're given pressures instead of moles. So guess what? We don't have to find the concentrations. We can use our pressures in our equilibrium expression. But we'll still need to use an icebox for this. We are going to use the quadratic equation in this one because our result in our E row are not going to be perfect squares, so we can kind of see how that works. Here's a refresher of your quadratic equation. You probably all don't remember it. From what year did you have quadratic equations? I don't remember what. But so we're going to be looking for the A term, the B term, and the C term, and we'll plug that into this expression, and then that will allow us to find what x is, which we then can use to substitute back into our E row to find our pressures. In this case, I think we're working with pressures. All right, so let's see what we've got here. So we've got a following reaction. What does that look like? Oh, shoot. I don't know that I've got it here, the following reaction. It is on page 630. We have hydrogen gas and iodine gas reacting to form hydrogen iodide gas. And what they've given us here is that in a 5-liter flask, which actually isn't going to be important for this because they've given us the pressures initially. So we aren't actually going to use the volume in the problem. It says we have hydrogen iodide present at this pressure, hydrogen at that pressure, and iodide at this pressure. So the thing that's a little different on this problem is we are not starting with equal initial amounts. The last problems we did, and that's one of the reasons why we ended up with perfect squares here. We don't have equal pressures starting off with. So it says find the equilibrium pressures of all the species. There's our equation. Okay, so we've got an eye on that. Okay, here is our equilibrium expression with the K, which is 100 here. We have initial pressures of each of these, so guess what we need to calculate? Got to determine our shift. So we are going to find Q. They've just listed the initial pressures there. Finding Q by using those initial pressures into our equilibrium expression. Q is 5,000. If you remember, K was 100. So when you compare K and Q, K was, what did I say? That was 100 was your K. All right, and then our Q is 5,000. Let's see if I can write it on the screen better. 5,000. So our sign comparing these numbers is a less than sign. So what that means is our direction of shift now is going to be to the right. So we are going to make reactants and consume products, which is different, which is good for you to see this. All right, so our products are going to decrease in pressure and our reactants are going to increase in pressure. So we're going to use our icebox here. Here's our equation across the top. Our I row, these were the given pressures. I know we don't have the labels in here, but these were all atmospheres here. Okay. It said nothing about how much the pressure was at equilibrium. It didn't tell us how much any of these changed by, so we have to assign an x to those changes. Again, I said find the ones that have a coefficient of 1 and assign them an x of 1. And then this is a coefficient of 2, so we make that 2x. So this is actually going down by twice the value as these are increasing. So now we've got the pluses on the reactant side and the minuses on the product side because we're shifting in this direction. So the pressure will increase by x for all of these and decrease here by 2x. So our K was 100. We're going to plug the E rho into our equilibrium expression. And it looks something like that. Notice we don't have a perfect square in the denominator. Actually, the top isn't a perfect square either, but our denominator is not a perfect square. So in order to go with this problem, we are just looking for x. Now, these are times signs, you guys. Times, not x's. So don't be confused by all those x's you see in there, okay? What we're going to have to do is just combine like terms and get everything in the form of a squared plus there it is, sorry, ax squared plus bx plus c. So we have to convert this into this form here. Why are we doing that? Because we need the a, the b, and the c to use in our quadratic, since this is not a perfect square and it's quite a messy math problem. All right, so that's what our goal is. I don't have all the work shown for this. It does take a while. It is very humdrum to do all that, but it's got to be done in order to help us find out what x is. So you may want to make sure that you can do all that math. I don't have it shown here. What I have is the result of converting all of this into our ax squared plus bx plus c equals 0. All right, so moving everything around, this is what we end up with. Here is our a value, our b value, and our c value. Those can thus be put into our quadratic equation and solve for x. Fun, fun, fun. Some of you have the quadratic equation in your calculator, which should make it really easy for you. You just plug all those in, a, b, and c, and I think it finds your x for you, doesn't it? Maybe. So once we do that, here is plugging all those values into our quadratic equation, and we get an x. Now, you probably are going to get a positive value and a negative value for x here. The negative value is going to be the one that you throw out. You want to look at the positive value for x. So if you do get your positive term and a negative term, just drop the negative x value and go with the positive x value. If they both end up positive, one of them is going to be larger than the actual possible change that can happen. So you would have to get rid of that term and go with the one that's actually smaller than the initial amounts of starting, the initial amounts there. If you don't understand all that right now, it's okay, because most of the time that's not going to be the case. When you're not going to use a quadratic a whole lot, I just want you to know that it's at times it does need to be used. Most of the time you'll have one of these answers being one positive and one negative, and you want to use the positive one. So this is our x that we actually solved for with the other problems using doing the perfect square. So then we got to take that x and go back to our ice box here and plug the x in here and see what our new pressures are. And that looks like this. So there's our pressure of our hydrogen iodide, which was our product, which actually got consumed and went down by 2 times the amount of x. So there's our new pressure. Our hydrogen went up, as did our iodide gas. They both went up. And so the green values here are reflecting the actual equilibrium pressures. Again, a good way to check. Take your equilibrium pressures you've just solved for, plug them back into your equilibrium expression, and see if you get the K. I think we said the K was 100 in this case. Yep, right here. So you can double check your work with that. All right, I know that was a lot, you guys. I hope you have a good weekend. I'll get this on Canvas soon with some book problems for you to practice. Take care. We'll see you Monday.